As we start the last chapter that we're going to cover, and we're only covering a part of this chapter, we're going to be looking at parametrizations of plane curves. And basically what this is going to do is it's going to define our x and y values as independent functions of time t. And the definition there says if x and y are given as functions, x equals f of t and y is g of t over an interval I of t values, and again that's time, then the set of points xy, which would be f of t, g of t, is a parametric curve. And those equations are parametric equations. So I've got a picture here, and this is tracing the path of a particle at time t. And you can even see that there's an arrow to show the direction of travel. So in this case, the particle would have traveled here in the bottom left and followed this kind of random curve. Okay, so again, x and y are defined as separate functions of time t. And that gives us these parametric equations, and then the graph is a parametric curve. So a few more definitions here. It says the variable t is called a parameter for the curve, and the domain of that is the parameter interval. It says if I is a closed interval where t is going to be between points A and B, then in the graph, f of a, g of a would be the initial point of the curve. So in this picture here, it would be the point here in the bottom left. And f of b, g of b is the terminal point, and that would be this point up here at the top in this example here. And it says when we give parametric equations and a parameter interval for a curve, we have parametrized the curve. The equations and interval together constitute a parametrization of the curve. You will not hear me use those terms a lot because I just think that they don't flow well, but that's what is happening here. And it says finally that the graph of any function, y equals f of x, can be given what's called a natural parameterization, x equals t, and then y equals f of t. So sometimes it's best to just look at examples to see exactly what is going on here. And that's what we're going to do. We're going to look at a couple examples. The first one says, given the following parametric equations and parameter intervals for the motion of a particle in the xy plane, identify the particle's path by finding a Cartesian equation for it. We're then going to graph that equation and then indicate the portion of the graph traced by the particle and the direction of motion, which is a mouthful, but it's not as bad as maybe it initially seems. So here we have some parametric equations. We have x and y defined in terms of t, and then we're given that interval that t goes from negative to positive infinity. So what I'm going to do is I'm going to rewrite this into just a regular Cartesian equation in terms of x and y. And this one is relatively easy to do. Since x equals 3 times t, I can redefine that, or rewrite that rather, as t equals x divided by 3. So I'm going to do that real quick. And now that I know that t equals x over 3, I can go into that second equation, y equals 9t squared, and replace t with x over 3. So we have y is equal to 9 times x over 3 squared. So y is equal to 9 times x squared over 9, or just y equals x squared. So in this case, we're just going to be graphing a parabola. Now, I'm just going to plot a couple of the standard points here on a parabola. This is going to open up. So it goes through the point 0, 0, negative 1, 1, positive 1, 1, negative 2, 4, positive 2, 4. And it would also hit negative 3, 9, and then positive 3, 9 as well. Since t covers negative to positive infinity, we don't have a starting or an ending point here. So I'm going to go ahead and just try to connect my dots as neatly as possible. So again, I don't have a starting or an ending point, but we do have a direction of motion. As t is negative, we're looking over here. So it's going to be moving down this way. And as t moves into the positive, we're going up this way. So we do have a direction of motion, which I'm just indicating with these little arrows. So the motion would come from the top left, follow it down, and then go up. So now let's look at a second one here. So here we do have a starting and ending point on our parameter interval. It says x is cosine of 2t, y is sine of 2t, and t goes between 0 and pi. Now, if you remember the trig identity that says that cosine squared plus sine squared equals 1, I'm going to apply it here. And I can say that cosine of 2t squared plus sine of 2t squared is equal to 1. So in other words, x squared plus y squared equals 1. So here we have a circle. Now, this is a circle with radius 1. Its center is at the origin, so it's just going to be this little tiny circle in here. But we need to pay attention here because we do have a starting and ending point. T will start at 0, and when t is 0, our x value is 1 and our y value is 0. So it's going to start here, and it's going to follow the circle all the way up until t equals pi. Well, that's going to end up being a complete circle because if we were to plug in pi for t, x would be cosine of 2 pi, which is 1. Y is sine of 2 pi, which is 0. So we're going to end where we started. So this is going to be a full circle. And again, it's going to start here at t equals 0. Sorry, that's really messy. And it will end at that same point. And again, making a complete circle.